An impulse train in the time domain will give you an impulse train in the frequency domain. And if we were to have a very tightly spaced impulse train in the time domain, it will give us a very widely spaced impulse train in the frequency domain. If we had a very wide spaced impulse train in the time domain, it will give us a very tight impulse train in the frequency domain. And this idea lies at the heart of something called aliasing, which we'll get onto in another video. But in this video we're going to just look at the impulse train and work out why it is an impulse train in the time domain gives you an impulse train in the frequency domain. So let's look at the impulse train. Now we have an intuitive understanding of an impulse train. We're going to have the time axis here, and we're going to have an infinite number of little spikes, and they're going to be separated by a particular period. Now the period here is given by large t. So from this spike to that spike, the period is t. From this one over to there, the period, that's going to be a distance of 2t, and so on and so forth up to nt. And the opposite direction here will be minus t, minus 2t, minus nt. So if we were going to represent this impulse train as a little function, we could start off with the impulse. Now the impulse is given by delta t, and we'll have a look at the impulse function just in a second. So we'll have this one here, which is delta t. Now the next one is going to be delta t delayed by a factor of t. So in order to delay the function by t, you simply take the delta t minus t. And if it's delayed by next function here, next spike will be delta t minus 2t, and then minus 3t, and up and so forth. And in general it'll be delta t minus nt. Of course, if we were coming the opposite direction here, it would be delta t plus nt. So if we wanted to represent this impulse train as a function, we would simply have to add up all of the individual impulses. So we'd have to add up all of these. So this is the function we end up with here. So it's going to be the sum from n equals minus infinity to plus infinity of delta t minus nt. And this is going to be our impulse train, which we'll call delta t of t. Now I've got that small subscript t there, it's just telling us that it's a time-based impulse train. So let's have a look at the delta function. This is sometimes known as the Dirac delta function. So the idea about this is that we have a spike that's infinitely high and infinitely narrow, and the area underneath the spike is given by 1. So obviously we don't represent the spike by an infinitely high value, we just represent it as the area. So we say the height of this is 1, but the 1 here actually represents the area under the spike. So this isn't a function as such, it's actually what would be called a distribution, but for all intents and purposes, for what we're interested in here, we'll just call it a function. So we can write this function down. We can say delta t, well, it's going to equal a value of infinity whenever t is equal to 0, and it's going to equal the value of 0 for all t not equaling 0. And the main point here as well is that the integral from minus infinity to infinity of our function delta t by dt equals 1. So that's telling us the area under this little function is a value of 1. And we can see how we're going to produce this function. If we had a little rectangular function and the height was, the length here was epsilon, then in order to make the area 1, the height there would have to be 1 upon epsilon, because epsilon cancels with epsilon, you get a value of 1. So if we were to look at halving this length epsilon, we'd have to double the height, and if we kept halving and doubling, then this thing here would tend towards a spike which is infinitely narrow, infinitely high, and it's got an area of 1. So we notice all we're doing here is we're using an even function in order to produce this. Okay, so we could use any even function. Here's another even function here. So we could look at a triangular wave, a triangular pulse, and if we were to halve the distance, we would have to increase the height to keep the area 1 as 1, and so on and so forth. And this thing here will tend towards a spike as well, and we could use a sinc function to do the same. So really what we're doing is, in order to produce this delta function, we're taking the limit as epsilon tends towards 0 of any even function, and it will tend towards this delta function. So we're interested in finding out the Fourier transform of our impulse train. Now before we find the Fourier transform of the full impulse train, let's look at just the Fourier transform of a simple impulse. So in order to get the Fourier transform, we'll look at it analytically and also in a little geometric sense. So analytically it's going to be the integral from minus infinity to infinity of our function, which is delta t e to the minus I omega t by dt. So this is the equation for our Fourier transform. It takes the time domain function and it transfers it to a frequency domain. So this is rewritten here. Now the thing to note here is that we know that delta t only exists at an infinitesimally small region next to the origin, and we also know that this function here delta t is an even function as well. So we can say that the integral from minus infinity to infinity of delta t by dt, which is just the definition of our impulse function, that area there, that is going to be a value of 1. So this leaves us e to the minus I omega t. Well, we know that this only exists at an infinitesimal region round about the origin, so it's really as t tends towards 0. So we could really just replace that t there with a 0. So that would be e to the minus I omega t, which would be equal e to the minus I omega times the t, which is 0, so it's just be e to the 0. Anything to the power of 0 is just a value of 1. So whenever we find the Fourier transform of a little impulse, we get a value of 1. So what does that really tell us? Well, it says that if we were to have an infinitely narrow, infinitely high spike, then in the frequency domain it's equivalent to adding up every single frequency from minus infinity to plus infinity. So let's look at this geometrically. Now you'll see this throughout the rest of the course, and if you've done the previous course on the Fourier and Laplace transforms, you'll be used to seeing this type of description. So I've done it in a little kind of three-dimensional sense. So we have our function here of time, so this is the time axis, and the function is delta t. And we have over here the frequency equivalent of this. So this is this function Fourier transformed. So we've got an omega axis here, and we know that the Fourier transform of delta t is a value of 1. So that's just 1. It goes off to plus and minus infinity. Now in order to go from here across to here, what we did was the Fourier transform, we integrated it and multiplied by e to the minus I omega t. Now we know that e to the I omega t is actually equal to cos omega minus I sin omega. But as we said before, this function here is a purely even function. So if we integrate an even function from minus infinity to infinity, we get a value. But if we integrate an odd function from minus infinity to infinity, we get a value of 0. So the sin omega t is going to be an odd function. The delta t is an even function, so even times odd becomes an odd. So it means that the sin omega t part of this here just disappears. It becomes 0. So in this instance here, what we have here is all that's left from the e to the minus I omega t is the cos omega t. So this here represents that cos omega t, and this is a cos omega t surface. So there's the omega axis, which is just this axis here. That's the t axis, which is this axis. This is a cos omega t surface, and it's modulated by this little spike. So the only thing that's going to be left of the cos omega t surface is this little central part here. Okay, and of course you're integrating it in that direction, so the only part of it is this here. So we're just basically looking in and taking the shadow of this here onto the frequency axis, so that gives us a value of 1. So I talked through that quite quickly, and if you have a look at a previous video when I talk about even and odd function, and I talked about the ethos of the type of derivations we're going to do in the three-dimensional graphical approach, then that will become more apparent to you. So now we know what the Fourier transform of a simple impulse looks like. We know we're going to create an impulse train, and that impulse train is made up of delayed impulses, so we delay it in time by a factor of the period t. So we're interested in finding the Fourier transform of a delayed impulse now. So we just write down in terms of an analytic derivation. Now also in a second we'll look at a graphical version as well. So we've got to integrate the function. Well, what is our function? Our function is our delayed impulse, which is delta t minus t. So this is our delayed impulse shown here. Well, it's delayed by a factor of t, and this is the height, delta t minus t. And when we take the Fourier transform, we integrate from minus infinity to infinity, e to minus I omega t by dt. Now, we know that the value here is only going to be a value of 1, that is the area here, integral from minus infinity to infinity of delta t minus large t by dt. Well, that's going to be a value of 1, okay, so that's just the area under the impulse. But the e to the minus I omega t, well in this instance here, this only exists at a point where t, that is the axis here, is equal to some value large t, which is just the delay. So that becomes e to the minus I omega large t. So that's just 1 times e to the minus I omega t. So that means that whenever we Fourier transform a delayed impulse, we get an exponential function in the frequency domain. Now we could do the same thing here with a function in the frequency domain. Whenever we delay a function in the frequency domain, it is equivalent to an exponential function in the time domain. Although we're not bothered with this for the moment, we could just look at the top one first of all. So let's have a wee look at that graphically, and it'll be more intuitively obvious whenever we see it in a graphical format. So what we have here is the time axis. So the bottom one is a function of time, which is just our delta function, which is delayed. In this instance here, we've delayed it by this factor of t1. And the drawing at the top, this is a Fourier transform of this delayed function. And the Fourier transform, we've done it graphically in 3D. So we've got the amplitude up here, and we've got the frequency along here, and we also have the imaginary part of the amplitude there. So this is the real part, and this is the imaginary part. Now, if we had just been looking at delta t, which was sitting at the origin, then this would be a straight line. So we just have a straight line going on from minus infinity to plus infinity. So we would have every single frequency of the same amplitude. Now, whenever we delay that impulse, the effect of delaying it has the effect of adding linear phase onto the frequency domain equivalent. So what happens in effect is that if we were to think about this straight line here as being made up of an infinite number of little phasors, then whenever we shift a function in the time domain, these phasors start to rotate, and you can see the rotation of these phasors here. So at the positive axis, the phasors start rotating in this direction, and in the negative axis the phasors start rotating in this direction. So what happens is you get this curving, and eventually you get a corkscrewing effect, and that corkscrewing effect is just the exponential function, the complex exponential function I should say. So that's it delayed by a factor of t1. So let's have a look and we'll see it delayed by a factor of t2. So we've delayed it by an extra factor of t2. So now what's happened is this straight line here, all the phases have started rotating, and you have this corkscrewing effect. So this here in effect is our complex exponential. Now if you've looked at the Fourier and Laplace transforms course, you'll have seen there's a full video on this complex exponential which shows this effect here of the corkscrewing effect. So you can see where we're going with this. We know that the delayed impulse is going to give us a complex exponential in the frequency domain like this, and we know we're going to create the impulse train by adding up lots of these delayed impulses, and they're all delayed by a particular period. Now you might look at that and think, well, it means in the frequency domain we're going to be adding up lots of these complex exponentials, which we are, and it looks initially like we're going to end up with some very complicated function. But it turns out that whenever we work out the Fourier transform of an impulse train, we actually get another impulse train in the frequency domain. So it's maybe not intuitively obvious why it is that whenever we add up all of these complex exponentials that we end up with another impulse train, just like this impulse train at the bottom here. Well, we're going to have a wee look at that next. So let's look at this graphically. Let's assume that we have an impulse train in the frequency domain. So this is our impulse train here. The period here is a value of omega s, and each of these components are going to be given by a number k, so it's going to be k omega s. So this is our omega axis here, and we've got our time axis here. So we're saying that if we Fourier transform an impulse, or if we inverse Fourier transform an impulse train, we'll get another impulse train. So in the time domain, we're going to have another impulse train here. So this is drawn out here, and the period of this is t, and each of these are going to be given by a value of nt. Now, if we think about just this impulse train here in the frequency domain, we can see that this is a purely periodic function, and it's a purely even function. So if it's an even function, it means that if we were to, say for example, go from the frequency domain back to the time domain, so we take the inverse transform of this, we're going to be multiplying this by e to the I omega t. But the e to the I omega t is made up of the cos omega and the sine omega, and we know that sine is going to be an odd function, so we're going to be multiplying an odd function with an even function, so we'll get an odd function. So whenever we multiply, so if we get an odd function, we integrate the odd function from minus infinity to infinity, it disappears. So the sine part of the e to the I omega t completely disappears because we're dealing with purely even function. So all we're left with then is the cos omega t surface. So this is the time axis here, and this is the frequency axis here. So we can see that what's going to be happening is, if we think about these small spikes here as modulating this surface, then there's only going to be a cosine term at each of these points. So for example, here's a cosine wave there, and this part of it just goes underneath, okay? And there's another cosine wave, and as we work down through along this axis, the frequency gets higher and higher, so the wave, there's a greater number of peaks and troughs because the frequency is a lot higher. So in effect, what we have here is a simple Fourier series. We're going to be adding up in this direction, so we're going to be adding up all of these frequency components in order to give us our time-based function. So let's look in from both directions. We'll look in from this direction in towards this surface, and we'll look from this direction in towards the surface. So we'll go from the frequency into the surface and from the time into the surface. So in the frequency domain, we simply have our frequency domain here, and we have our impulses. So that's our little discrete impulses, which makes up our impulse train. Now whenever we look in from the time axis, we're going to see all of the cosines. So that's just all of the cosines that we've seen in the previous drawing. So that's us just adding up all of these cosines we're looking in here, and we're just seeing each and every one of these. And in order to create the time domain function, we're going to have to add all of these up. But there's a nice neat way of adding these up that helps us show that the summation of all these cosines is actually going to be an impulse train. And the way we do that is by noting that the surface above is going to be symmetrical. So let's have a little look at that surface again. So a lot of the stuff you get from this comes from this surface. So if we note here that if we wanted to add up all of these cosines, you can see that there's going to be, first of all, this one in the centre is not a cosine, it's just a value of 1. Okay, so we're going to have 1 plus all of the cosines. But all of the cosines at this end here are equal to all of the cosines at that end there, because it's a cosine is going to be purely symmetric. So what we could do is we could add up everything from this side here and then just double it, and we'll actually have the same result. So we're going to have 1 plus 2 times the sum of all of these cosines. So it's going to be 2 times the sum of the cosines, and the cosines are going to be given by cos k omega s t. So we've got this final function down here. So the summation of all these cosines is in effect 1 plus 2 times the sum from k equals 1 to infinity of cos k omega st. So let's go ahead and we'll have a look at this in a graphical calculator, and we'll see how the summation of all these cosines gives us an impulse train. So I've put the function in this graphical calculator. Now the nx here, that's just the same as our k cos omega st. So if I was to change the value of k, it just adds more and more of these cosine functions up. So that's the second one added and the third one. Now you can see here that the energy is starting to be concentrated in just single points. So I'll let this play out and you can see how this creates an impulse train. So you can see all of the energy created is focused at one point along the axis here. So we're creating in effect another impulse train by adding up all of these cosine functions. So we can see geometrically here why it is that when we look at an impulse train in the frequency domain, it gives us an impulse train in the time domain, or equivalently an impulse train in the time domain will give us an impulse train in the frequency domain. And we can see that because the impulse train is a purely even function. So that means that whenever we do the Fourier transform or the inverse Fourier transform, we have to multiply it by either e to the I omega t or e to the minus I omega t. But the e to the I omega t is made up of a cos omega and a sine omega. Now the sine function is an odd function, so we multiply this odd function with this even function, we get an odd function, and whenever we integrate that odd function from minus infinity to plus infinity, the sine part of that e to the I omega t just disappears. It is equal to 0. So we're only left with the cosine part here. And then if we were to add up all of this cosine components, they're all of the equal height. And we've seen when we add all of those up, we just get all of the energy focused at individual points. So therefore, an impulse train in the time domain will give us an impulse train in the frequency domain. So we know intuitively and graphically that an impulse train in the time domain will give us an impulse train in the frequency domain. So let's look at this analytically. So we know that an impulse train in the frequency domain is going to be a purely periodic function. So if it's a periodic function, we must be able to find the Fourier series of it, and we can find the Fourier series from this equation here. So we take the f of t and we replace f of t with our impulse train in the time domain. So the impulse train in the time domain is given by this little function here. So we're left with this function. Now this looks a bit scary, but it all simplifies it quite easily. So if we first note that we're integrating over just the one period here from t upon 2 to minus t upon 2. So it means that this whole function here, which is the impulse train, all we're interested in is one of the terms, and it's the term that sits at the origin. So it means that this delta t minus nt can simply be replaced with our delta t. Now we also note that delta t is only defined at the origin, so it means that we can take the limits of integration here from t upon 2 to minus t upon 2 and extend them out to plus infinity to minus infinity. Now we know from the definition of our delta t that the integral from minus infinity to infinity over delta t by dt is just a value of 1. And we know that this is only defined at t equals 0. So it means that e to the minus k omega st is just going to be e to the power of 0 because this value t here is 0. So we'll just be left with the 1 upon t, e to the power of 0, anything to the power of 0 is just 1. So we're just left with this value 1 upon t. So therefore we can take this 1 upon t and put it back into our equation up here. So we'll just be left with f of t equals 1 upon t, the sum from e to the ik omega st. But we note from this that a complex exponential in the time domain is equivalent to an impulse in the frequency domain. So we're adding up all of these complex exponentials to give us an impulse train in the frequency domain. So that impulse train in the frequency domain is going to be given by delta omega minus k omega s, and it's the sum from k equals minus infinity to infinity. So there's one other thing to take care of here. There's actually a 1 in front of this e. So this 1 is just going to give us an amplitude. But the Fourier transform of 1 is going to be a value of 2 pi. So it means that down here we're going to have our 2 pi upon t, but 2 pi upon t is just a value of omega s. So finally we're left with this transform pair here. This tells us that an impulse train in the time domain will give us an impulse train in the frequency domain. Now the thing to note here is that the period of the impulse train in the time domain is given by t, and the period of the impulse train in the frequency domain is given by omega s, and we can see that omega s is equal to 2 pi upon t. So if t is very large, then the value of omega s is small, or if t is very small, the value of omega s is very large. So what this tells us is that if we have a very tightly spaced impulse train in the time domain, we'll have a very wide spaced impulse train in the frequency domain. Equivalently, if we have a very wide spaced impulse train in the time domain, we'll have a very narrow spaced impulse train in the frequency domain. And this relationship between the period of an impulse train in the time domain and the period of an impulse train in the frequency domain lies at the heart of something called aliasing, which we'll get on to in a later video.